Welcome back to the deep dive. You know, uh, Usually when we sit down here, we're peeling back the layers on something abstract,
Hmm.
like a historical event or a social trend.
Right, maybe an economic theory or something.
Exactly. We take a topic, strip it down, and see what makes it tick. But today, we are doing something a little more literal. We are quite literally stripping down a machine.
Yeah, we are.
We're looking at the Iron Man suit.
And I want to be clear right off the bat here, because I know we have listeners who are diehard Marvel fans, and they might be sharpening their pitchforks right now.
Pitchforks down, everyone.
Pitchforks down, please. Because this isn't a movie review. We are not here to critique the CGI or argue about MCU plot holes. We are treating the Iron Man suit as a legitimate case study in engineering.
I love the phrase used in the research notes for this. They described it as near-future ergonomics.
Right.
Which honestly sounds like we're discussing a really expensive office chair.
It does sound like that.
But we're actually talking about a weaponized flying suit.
A very high-end office chair. But it's also this fascinating cultural touchstone. I mean, the source material points out that the character of Tony Stark represents a massive shift in pop culture. Think about how we used to view scientists.
Oh yeah. Before Iron Man, Hollywood scientists were usually the timid, bespectacled geeks in the lab coats.
Exactly.
The guys who get bullied until the hero finally shows up to save them. They were always the sidekicks.
Never the main event. But Stark breaks that mold entirely. He's charismatic, he's confident, the notes call him a hit with the ladies. He effectively made engineering cool again.
He really did.
But our mission for today isn't to analyze his personality, it's to dismantle his invention. We want to know if his science is actually cool or if it's just magic wrapped up in red and gold metal.
And we have a massive stack of research here to help us figure that out. We've got physics calculations of specific movie scenes, material science breakdowns, and real-world military exoskeleton reports.
It's a lot of data.
It is. So we're going to dismantle this suit piece by piece. The materials, the physics of that famous crash in the desert, the mind control systems, and that infinite power source.
We want to separate the plausible from the impossible. And honestly, some of it is surprisingly plausible.
So let's start with the shell. The look is iconic, right? The faceplate, the hot rod red paint job. But here is the very first bubble we have to burst, and it's literally right there in the name. Iron Man isn't actually made of iron.
No. Honestly, if he were, he wouldn't even get past the driveway.
Too heavy.
Way too heavy. Iron is a terrible material for a high-tech flying suit. It's dense, it's incredibly heavy, and it creates a major maintenance nightmare because it rusts.
Right.
Plus, it's actually softer than steel. So if you built a flying suit out of pure iron, you're basically building a heavy, rusty coffin.
So look at the evolution in our sources. The Mark I, that bulky, trash can-looking suit he builds in the cave that actually was scrap metal.
Yeah, the Mark I was scrap iron, copper, leather. It was essentially a glorified tank you wear. It stopped bullets, sure, but it moved like a tractor. As the suits evolved in the films, Stark supposedly moved to titanium alloys. But the research highlights something really specific here called single crystal titanium.
I saw that in the notes. Now I know titanium is strong and light. That's why I paid extra for my fancy camping spork.
Naturally.
But what is the single crystal part? Is that just sci-fi jargon they threw in to sound smart?
It totally sounds like it, doesn't it? But it's very real. Think about standard metals. At a microscopic level, most metal is made up of grains.
Like sand.
Sort of, lots of tiny crystals all smashed together. And the boundaries between those grains are weak points. If the metal is going to crack or fail under stress, it usually starts right there.
Oh, like the mortar between bricks.
Exactly, perfectly put. Now, single crystal means the entire piece is grown as one continuous structure. There are no boundaries.
So no weak points.
No weak points at all. In the real world, we use this in the aviation industry, specifically for the turbine blades in jet engines.
Wow.
Yeah, they have to spin at thousands of RPMs and withstand immense heat and physical impact like bird strikes without shattering.
Which is actually a super relevant use case for Tony Stark.
Yeah.
I mean, I don't recall him hitting a pigeon at supersonic speeds in the movies, but if he did, normal metal might just shatter.
Right.
Single crystal titanium wouldn't.
He's definitely prepared for the pigeon strike. But there's another material mentioned in our notes that I think is even more fascinating. It's called nitinol.
Nitinol, that's the nickel titanium alloy, right?
Yes. The Ni is nickel. T is titanium, and NOL stands for Naval Ordnance Laboratory, which is where it was discovered. The magic of nitinol is that it has shape memory.
Okay, explain that, because in the notes it says the suit can quote-unquote heal, which sounds very video gamey to me.
It does, but it's not biological healing, it's thermal. Nitinol has 2 different crystal structures depending on how hot it is.
Okay.
So you can mold it into a specific shape, say the curve of a breastplate at a really high temperature. Then when it cools down, you can bend it, dent it, smash it with a hammer.
And it stays dented.
It stays dented. But if you
Oh.
heat it up again past its specific transformation temperature, it literally snaps back to that original shape.
That is wild. So if Iron Man takes a missile to the chest and the armor gets dented, the heat from the explosion, or even just the heat from his own thrusters, could theoretically cause the metal to just pop back into place.
Theoretically, yes. It effectively heals the dent. And we use this in medical stents today. They compress them to put them into the artery, and then your body heat makes them expand back to their original size.
That is incredible. It's like the metal has muscle memory. But a suit isn't just about the raw material. It's also about the construction.
Yeah.
I was reading through the structural analysis in our sources, and it compared the suit's layering to a Japanese katana sword,
Yes.
which seems like a strange comparison for a high-tech robot suit.
It might seem strange, but it's actually a brilliant analogy for understanding how you protect a soft human body inside a hard shell. A katana isn't just one solid piece of metal. It uses this technique where you have a V-shaped hard outer layer called the han. That's for cutting and stopping other blades. But if the whole sword were that hard, it would be way too brittle.
It would snap on impact.
Exactly. So the core of the sword is a softer, more ductile metal called kawagani or shigan. It absorbs the shock.
Okay.
The notes actually contrast this with Batman's armor. Batman wears what they call a sports shirt setup, Kevlar, Nomex, flexible plates. It protects you from the penetration, but you definitely still feel the hit.
Whereas Stark's suit is described as a monocoque or an integrated unit.
Right. It relies on multi-layer cladding. You have the titanium alloy on the outside to stop the bullet, and then layers of vibration-dampening materials on the inside to handle the energy. You desperately need that ductility.
Because if the suit were perfectly rigid,
100% of the energy from a punch or a crash would transfer straight through the metal and directly into the person inside.
ouch. Which brings us to the reality check. We've been talking a lot about the movie version. But do we have real exoskeletons? Because I've seen videos of soldiers wearing these metal frame things, but they don't look like Iron Man. They look more like...
Like hiking gear on steroids.
Yes, exactly.
That's a fair description. We aren't at the flying tank stage yet, but the tech is real and it's very active. Lockheed Martin has a suit called the HULC. HULC.
That is a great acronym.
It really is. It stands for Human Universal Load Carrier. It's hydraulic powered. And the main purpose isn't to make you punch through brick walls. It's to make you a really efficient pack mule. It allows a soldier to carry 200 pounds of gear for extended periods without fatigue.
So it takes all the weight off the back.
Completely. It transfers the weight of the backpack through the titanium frame, down the legs, and straight into the ground. The soldier barely feels it. And there's another one called the Forbus, which is designed for shipbuilders.
To hold heavy tools.
Yeah, like giant grinders. It holds them so they feel totally weightless to the worker.
And I saw a note about a Japanese version, too.
Yes, the HAL Hybrid Assistive Limb. That one is actually entering the commercial market right now for construction and elder care. So the wearable robot part of Iron Man, that's actually the most grounded part of the fiction. We are doing that right now.
Okay, so we can build the shell. We have the fancy titanium. We have the hydraulic frames. But here's where the deep dive gets really interesting and significantly more painful.
Oh, yeah.
The physics of actually using it.
Yes. This is where the fantasy really starts to crack under the weight of Newton's laws.
We have this specific analysis in the notes of the escape scene from the very first movie. Tony is the Mark I, that heavy scrap metal suit. He launches from the cave, flies for about 4 seconds, runs out of fuel, and crashes into the desert sand.
Right. And in the movie, what happens? He groans, pulls himself out of the crater, and basically just walks away.
He's a little dusty, maybe has a mild limp, but he's fine.
But let's look at the math provided in our source material. First, let's talk about the mass. The estimated total mass is 750 kilograms. That's Tony plus about 680 kilograms of scrap metal armor.
That is a remarkably heavy object to get airborne.
It really is. Now, the boots provide thrust. Based on the flight time and the trajectory we see in the film, the analysis calculates that those boots are putting out about 4.8 Gs of acceleration.
4.8 G, is that survivable for a person?
Totally. Fighter pilots take up to 9 G for short bursts. Roller coasters hit 4 or 5 G all the time, so the launch, totally plausible. The boosts work.
It's the landing that worries me.
And it should. Based on the height of the fall and the mass, the suit hits the desert ground at approximately 342 kilometers per hour.
342 kilometers per hour. That's fast.
Fast. To put that in perspective for you, the top speed of a Lamborghini Aventador is roughly 380 kilometers per hour. So imagine driving that Lamborghini at almost top speed and driving it directly into a solid brick wall.
Woof. Okay, well, that paints a picture.
And it gets worse. When we look at the kinetic energy, the energy that needs to be dissipated upon impact, it's calculated at 3.4 million joules.
I always struggle to visualize joules when they get up into the millions. Give me a comparison for that.
Okay, think of a 10-millimeter pistol bullet. It's a heavy round, carries a lot of energy. That crash in the desert has the energy equivalent of 3,217 of those bullets hitting you at the exact same moment.
Oh, wow. So Tony is dead.
In reality, absolutely. There is no question. The source analysis concludes that without some magical level of shock absorption, we are talking theoretical hydraulic dampers in the spine, the armpits, inside the helmet. The suit might survive, but the occupant just turns to jelly.
Jelly.
Liquid. This is the thing movies always get wrong. Deceleration. It doesn't matter how hard the outer shell is. If the shell stops moving instantly, your body inside is still traveling at 342 kilometers per hour until it hits the inside of the suit.
Right.
And then your internal organs are traveling at 342 kilometers per hour until they hit the inside of your rib cage.
So the katana layering we talked about earlier, that soft inner lining, that wouldn't be nearly enough.
Not for that amount of energy, no. That lining helps with a punch or maybe a fall from a second story. It does absolutely nothing for a terminal velocity crash.
So note to self, if I ever build the suit, pack extra padding. Or I guess just don't crash.
Avoiding the ground is definitely the primary survival strategy here.
But assuming we survive the landing, or we just learn to fly better, we have another huge problem. How do you drive this thing?
Right.
There's no steering wheel, there's no joystick. In the movies, he just kind of thinks it, he looks, the suit shoots.
And this brings us to the brain-machine interface, or BMI. This is honestly one of the most exciting fields in modern neuroscience, and Ironman is a fantastic example of where it could eventually go.
In Iron Man 3, there's that scene where he summons the suit pieces, they literally fly onto him, and he mentions he has 48 micro-repeater implants in his body to connect to the suit.
That's the sci-fi version, of course. But the core concept is rooted in real research. A BMI is basically a communication hub. It translates brain signal, your electrical impulses, into digital commands that a machine can actually understand.
And we can do this today.
We can. The sources detail a really specific experiment involving a monkey with a spinal injury. The monkey couldn't move its leg at all.
Okay.
Researchers used a wireless brain-spinal interface. They put a chip in the brain to read the I want to walk signal, bypass the spinal injury completely, and beamed that signal to a stimulator in the spine below the break.
And the monkey walked.
The monkey walked. It bridged the biological gap with the digital signal.
That is just incredible. So if we can bridge a gap inside the body, we can bridge a gap from the body to a suit.
Exactly. And it's not just for walking either. Professor Bin He at the University of Minnesota created a helmet, completely non-invasive, by the way. Just a cap with sensors that lets users move a cursor on a computer screen just by thinking about it.
Literally mind control.
In a way, yeah. It detects the electrical signals of neurons associated with motor tasks. You imagine moving your hand right, the sensors pick up that specific firing pattern, and the computer moves the cursor right.
This sounds a whole lot like what Elon Musk is doing with Neuralink.
It is the exact same principle, but Neuralink aims to take it much further. They are looking at the neural lace concept. The goal there isn't just medical. Fixing spines or helping paralyzed patients communicate is noble, of course. But Musk has spoken about a merger of biological intelligence and machine intelligence.
Which sounds very Tony Stark.
It really does. The idea is to enhance memory, decision-making, and processing speed. If you apply that to the Ironman suit, it solves the reaction time problem.
The reaction time problem.
Think about it. If you are flying at supersonic speeds, you can't rely on your hands to hit buttons. By the time your eyes see an obstacle, process it in your brain, and tell your hand to move the stick, you've already crashed into the mountain. The biological lag is just too long.
So you need to remove the middleman.
Exactly. With a neural lace, you aren't piloting the suit. The suit becomes an extension of your own nervous system. You feel what the suit feels. You move it like you move your own arm.
It's really the only way it could work. You have to be the suit.
Precisely.
There's another aspect of the control system that I found really interesting in the notes. The friendly bots.
Oh, yeah.
The emotional connection Stark has with his machines. Like that robot arm in his lab that's always messing up. He talks to it like it's a bad dog.
Ah, yes, the Roomba effect.
The Roomba effect. Is that an actual scientific term?
It's a real psychological phenomenon. People buy those robotic vacuum cleaners, Roombas, which, let's be honest, are just plastic discs that eat dust. But
Yeah.
people start treating them like pets.
Guilty.
See, people name them, they talk to them, they feel genuinely bad if the robot gets stuck under the couch.
I am definitely guilty of that. I named mine Dustin. And I swear I feel a little pang of guilt when I accidentally kick him in the hallway.
Exactly. And it raises an interesting question about human-robot interaction. In the movie, Stark's bots are technically just tools, but they act like teammates. NASA is actually studying this right now. Really? Yeah. Should robots be designed as tools or as teammates? If you're on a long-duration spaceflight to Mars, having a robot that you can bond with emotionally might actually be crucial for your mental health.
So Jarvis isn't just a user interface. He's an emotional support animal made of code.
In a way, yes. It changes the dynamic of the pilot. You want alone in the suit.
Okay, so let's recap where we are right now. We have the titanium shell, single crystal so it doesn't shatter on impact. We have the neural link to control it seamlessly with our thoughts. Now we just need to turn it on. We need to talk about the glowing circle in the chest.
The ARC reactor.
The ARC reactor.
The heart of the machine. And unfortunately, this is where our reality check hits a massive brick wall. This is by far the most unrealistic part of the entire lore.
Don't tell me that. I really want a chest flashlight.
I'm sorry to ruin it for you. But according to the lore, that little hockey puck-sized device in his chest is a miniaturized reactor generating 8 gigajoules per second.
8 gigajoules per second. Now, is that a lot?
It is roughly the combined output of 3 full-size nuclear power plants.
Oh.
All condensed into something the size of a drink coaster.
Okay, well, when you put it that way, it sounds a little absurd.
It breaks physics on a few different levels. First, the energy density is just impossible. We don't have any fuel source in the universe that can store that much power in that small a space. But the bigger issue, which the experts point out in the sources, is heat. Thermodynamics is a harsh mistress.
The waste heat from generating all that power.
Exactly. No energy conversion is 100% efficient. Even if you could somehow generate that much power, the waste heat would be astronomical. Stark wouldn't just be Iron Man. He'd be Molten Man.
He would be roasted alive inside the suit.
Instantly. And we don't see any massive cooling towers or radiators attached to the suit in the films. In the real world, high-energy systems require massive cooling infrastructure.
So what are we using for real flying suits? Because I know people have built jetpacks. I've seen the guys flying around stadiums and stuff.
We have things like the Solo Track and the Rocket Bell. The Rocket Bell was built by Stuart Ross, and it can lift a person about 2,500 meters in the air.
That's pretty good.
It is, but the problem is always fuel.
It's the weight, right?
Exactly. It's the tyranny of the rocket equation. To fly for a long time, you need a lot of fuel. Fuel is heavy. To carry the heavy fuel, you need a bigger engine. A bigger engine is heavier. So then you need even more fuel to carry the engine.
It's a vicious cycle.
It really is. Iron Man cheats this by having a magic battery with infinite energy and basically zero weight. That is the one piece of tech we are nowhere near replicating.
So until we invent a cold fusion hockey puck, we are grounded.
Or we are limited to very short, very loud flights using jet fuel where you have to carry everything on your back.
Well, this has been quite a roller coaster. We've dismantled the suit, and I feel like we have a real mixed bag of reality and fantasy here.
We definitely do. Let's look at the inventory. Materials. We actually have them. Titanium alloys, nitinol with the shape memory that's all real. We can build the shell today.
And the exoskeleton frame.
Real. The HULC and Fortis suits prove we can carry heavy loads using hydraulics. We can bear the weight of the armor.
The control system?
We are getting there. BMI and Neuralink are rapidly closing the gap on mind-machine integration. The idea of controlling a suit with your thoughts is no longer pure fiction.
But the survival and the power.
That's where we hit the wall. We completely lack the shock absorption technology to survive a superhero landing. Physics says you just turn to jelly. And we definitely lack the portable, infinite power source to run the repulsors and flight systems without melting the pilot.
But you know what strikes me is that the suit isn't just a weapon in this context. It's exactly what the research called it at the start. It's the ultimate near-future ergonomics.
It is. It represents a fundamental shift from wearing technology to integrating it. We are moving from holding a phone in our hand to potentially having the interface woven directly into our neural pathways.
Which is incredibly exciting, but also a little terrifying.
And that raises the big question I want to leave you with today. The source material touches on the ethics of this whole thing. Right now, BMI tech is largely focused on helping people with disabilities, making the blind see, helping the paralyzed walk. That is noble and obviously necessary.
But Stark uses it for enhancement. He doesn't have a disability. He just wants to be a Superman.
Exactly. When we move from therapy to enhancement, when we merge our brains with computers not to fix a break, but to make ourselves, quote unquote, better than human, are we ready for the moral implications of that?
It changes the whole definition of us.
It does. If you can download knowledge or control machines with a single thought, are you still just a human? Or are you something else entirely?
That is a very heavy thought to end on, but a necessary one for sure.
Yeah.
We might not have the ARC reactor yet, but the brain chip is coming a lot faster than we think.
It certainly is.
Thanks for diving deep with us today. We'll catch you on the next one.